Okay, we will start off by discussing what is signal processing, because whenever we are taking a course, it's important for us to understand at least the broader picture of it when you go into the real world. So to answer this question, we'll divide it into two pieces which were studied in the previous class. And the first piece is to address what is signal processing. We have to address what is a signal. So a signal is anything, and the things are in double quote because it could be literally anything, right? An image, if your shirt has some message, even that is a signal. So anything that carries information or conveys information is a signal. Now, there are two types of signal broadly that you can divide the world into. One is natural signals, or those that come from physical phenomenon. And the second type is man-made or synthetic signals. Okay. So what are some examples of these two classes? I have some examples listed down. Of course, you can find your own examples and think about them. So voice or speech, that's the seismic activity that was mentioned in class. We have climate parameters like temperature, pressure, again mentioned in class. We have what we are looking at, the visual scenes. I'm looking at you guys. It's a 3D signal. And countless other examples that you can work out. Now, what are the examples of man-made or synthetic signals? Once again, you can think of many examples of man-made signals. I'll give you some examples which are more aligned with our digital world, which you may or may not have sort of thought of. But for example, the counts of likes on a Facebook post, that's a signal. It's just counting how many likes you got on a post. It's telling you how popular it is or not popular. Frequency and time of searches on Google. That gives you information. It gives you information about the user. That's the sort of information that Google uses, for example, to display ads, to figure out many other things. Timings of a tweet. So most of the examples that you guys had described, they are perfectly valid man-made signals. Things that came up were, for example, Morse code or radio waves. But you also can have signals which are purely digital to begin with. What is being searched, Google keeps track of that. That's valuable information for advertisers. When calls are made, where they are made, that's valuable information to, for example, intelligence agencies. So if we understand what is a signal, then what is signal processing? While there is no universal definition, the way I'll describe it is, so we said a signal is something that carries information, and signal processing is extraction of useful information from signals and or it could be either one of these things, manipulation of signals to produce desired outcome. So let's take the examples of some of the things that we have mentioned earlier. Let's see what does signal processing do to those signals. For example, seismic activity or seismic vibrations. That's a signal. Now, signal processing can be used to extract valuable information and try to address questions like the following. Is a tsunami coming? This is now a big part of an effort where sensors are being thrown into ocean and figure out when an earthquake happens whether the situation is right that you will end up with a tsunami. That's signal processing. If it is coming, then where will it impact the most? So it starts with a signal and it's trying to address certain types of questions, extracting useful information and so forth. Now, the other type we talked about is voice or music. Again, signal processing can be used to generate. So the first example is you're trying to extract information. The other example is you could manipulate the signal to produce desired outcome. So you have a song that you don't like the bass or the treble on that song, and you do some signal processing to generate something that has, let's say, higher bass or treble. In technical language, signal processing, when it's done like that, we tend to call that an equalizer. We vary the different frequencies to figure out, to produce the desired effect. Now let's look at another type of a signal, which is pure digital or to begin with, and of course we'll look at the definition of what digital means more closely later. What kind of information can be generated from that? Well, Facebook uses that information to figure out what ads to display. So from the data, you do some processing to try to address what ads should I be displaying to the audience, or what other posts should I be displaying. So if signal processing is about extracting information or manipulating signal, the question is how to extract information or manipulate signals for desired outcome. And the first thing is there is no universal recipe. We looked at different examples: voice, Facebook data, seismic activity. What you do with the data depends upon the signal and the desired information that we are interested in. So really, the how to question depends upon the signal and the desired information or effect. So broadly speaking, we can say that signal processing is actually a large collection of tools where each one is suitable for specific tasks and specific types of signals. And there is no one single class that can teach you about all possible types of these tools, about all possible types of signals. So what is this class about? In this class, we look at a very, very tiny fraction of the world of signal processing. The idea is to introduce you to the basic concepts, give you certain tools that can get you started, and then if you feel interested, you have to take many other courses to really become an expert in signal processing. Okay. Now, most of the times when I talk to students, some of the confusion that come up is how is this signal processing different from some other fields that they have heard about. So I just wanted to touch upon that. In terms of connections, at least the modern signal processing has a large overlap with a number of fields, and those fields include machine learning, in which you basically train digital systems to learn about the tasks that humans do, like figuring out whether teaching a computer to tell when it looks at a picture, whether it's glass or some other tool that it's looking at. It has connections to statistics. There is a whole field of signal processing which is called statistical signal processing, where you have to learn more about probability and random processes. It has connections to applied mathematics and so forth. In fact, if you look around yourself, you'll be hard-pressed to find devices that do not use signal processing inside them. You can start with, for example, medical things, MRI imaging, CT imaging, modern X-ray. They all employ signal processing. You can look at your cell phone. Pretty much most of the tasks, other than the communication task, they rely upon signal processing. You are speaking, it takes your voice, digitizes it, and does some processing, compresses it, sends over or the radio waves and so forth. You take pictures with your cell phones. There's signal processing going on there, and it's it's really hard in today's day and age to find a device which is not using signal processing inside it in some way, shape, or form. Okay? So the message that I want to convey through this introductory discussion is really to make you realize, even though what we'll later be doing, it involves a lot of math, but in reality, it is one of the most ubiquitous fields of electrical engineering that you find around you everywhere. The reason you don't hear that much about signal processing is because signal processing at the end of the day is always helping you in some application. So you have to figure out what application you are interested in, and then signal processing comes into play. If you are into medical imaging, then there are different tools that you need to use for that. If you are into building cameras, there are different tools that you need to build for that. But they are all using some version of signal processing to achieve their objectives. So having tried to convince you that signal processing is everywhere, let's look at a simplest picture of what a signal processing system might look like. We'll, of course, expand that further as we go on. But the simplest picture is that you have signal or signals that are coming into some system, and then you have a processing block and then you produce some output or outputs. So you have, for example, if you are dealing with a digital camera, you press the button, photons come in, they land on the CCD sensors, they generate some electricity or voltage. Now that's the input signal. And now you're going to process it to generate a nice looking picture that you are looking at. So input, a processing block, output. That's the most general form of signal processing. Now, in the signal processing language, this processing block is given a certain name. So that processing block in the electrical engineering or signal processing parlance, that's called a system. So what is the technical definition of a system? So a system is anything that takes some inputs and generate some outputs is a system. It's a very, very broad term. Now, a system itself can have many subsystems. A system can be made up of a cascade or a combination of other systems. We can call them subsystems or whatnot. And just like the signals, we can differentiate in systems by dividing them broadly. There are many distinctions, but broadly I can say that there are systems which are natural, and then there are systems which are man-made. So let's look at examples of the two. For example, a natural system is our brain. What's the input to the brain? Electric firings of the neurons and stuff like that from our senses. Right? So the senses provide inputs, and then the output is actions. I'm moving forward, my eyes see an obstacle, they send electric current to my brain says, look, you gotta avoid that, otherwise you're gonna fall. I turn around or go some other place, right? So that's an output. A system which is man-made that you use all the time, hopefully not during classes, is cell phone. So again, there could be many inputs to the cell phone. The classical one is, well, you have a voice, which is input. So you have cell phone, you're talking, the voice is the input to the signal, and after a bunch of processing, what is generated out of the cell phone? Radio waves that get transmitted to the base station, and then they get transmitted to another cell phone and so forth. So radio waves are the output. So we have addressed then what is signal processing. Now this class is called digital signal processing. So let's ask ourselves, what is digital signal processing then? Now, signal processing in which all the processing takes place inside a digital system. And that digital system could be a processor, it could be a microcontroller, or any other similar device. That is what we'll call digital signal processing. So digital signal processing effectively requires digital hardware and also software which will implement the processing, the algorithms, and so forth. Okay. So some of the examples that we did are not necessarily of digital signal processing. Our brain is not a digital signal processor. The processing is not happening in a digital system. So, whereas a cell phone, or at least the modern day cell phones, are implementing digital signal processing. You talk about the processors in your iPhone, or your Samsung phones, they got the new Snapdragon from Qualcomm or whatever. Right? Those are basically processors, and why do you care about faster processors? Because that's what is going to carry out many of the processing things that are on your cell phone. Now, that is not to say that DSP systems cannot have analog components. DSP systems, in fact, most DSP systems, unless you are talking about, for example, Google or Facebook, most DSP systems, they can have analog components. But the purpose of these analog components is not to do processing. Their purpose is to interface the analog world . with the digital world. And they do not do processing. So if you have a cell phone, taking that example, when you are speaking, your voice is an analog signal. You need to convert that into a digital signal so that the processor inside your cell phone can do some sort of processing on it. So that device, which we'll learn later, analog to digital converter, it is interfacing the analog world, which is most of our, at least real world outside the computers, is analog. It is interfacing that analog world with the digital world. And similarly, when you are ready to generate something out, for example, through speakers, again, you are doing the reverse of that. You are taking some digital data, converting it into analog so that you can hear it. That's again an analog component. But the purpose of these two components is to interface the digital and the analog world with each other. It's not to do processing. You can have hybrid processing systems where some processing happens in digital, some happens in analog. But when you talk about DSP, that specifically means all the processing is happening inside a processor, microcontroller, or whatever. Now, the opposite of DSP is analog signal processing, which involves analog components for processing. What are those components? The usual resistors, inductors, capacitors, and so forth. So analog signal processing, of course, exists, but over the years, we have stopped doing analog signal processing. We have moved more and more and more towards digital signal processing. For example, there used to be analog radio station. Now they are all converting to digital radio station. There used to be analog TV stations. Now they are all digital TV stations. So the question is then, why do we prefer DSP over analog signal processing? And there are some really good reasons for that. Some of the advantages of DSP systems, they are not all inclusive, is, as was said, repurposing of the same hardware for different applications. And the reason is you only have to change the software. So the same Qualcomm processor, for example, Apple can use it in a different way. Samsung can use it in a different way. Same processor. What is different? Software. So that's where, and that's where it brings down the cost. The other thing is, if you make an error in your system, which invariably will be made, any errors, I'm talking about errors in the system, not errors in signals. Any errors in the system can be easily fixed and improvements can be made simply via software changes. The third important point is that digital systems up to a certain level, if you run them today, if you run them tomorrow, if you run them 5 days from now, their operating characteristics stay the same up to a certain level. Whereas analog components, we know that the resistance changes with temperature, the function of capacitance and inductance, they all are functions of different environment variables, and they change. They don't stay exactly the same. So operating characteristics of the system stay the same for most of the time. Most of the time, of course, beyond a certain limit, even your processor will break down. And the other thing is that storage, as long as you have the right storage, replication of information, storage of signals can be done more easily because of the digital nature. Now the question is then, is DSP all good, or are there any disadvantages of DSP? And the answer is actually there are disadvantages of DSP in the strict sense in certain cases. So the first disadvantage is if the signal that you are operating on if the signal that the DSP system is originally analog, then it first needs to be converted into the digital domain before you can process it. And that process is called sampling, which will be a major theme of this course. And sampling always entails some loss of information. So if you are using, for example, if you are a music producer and someone is recording the music, if you are not careful, there will be some loss of information. So that's why we talk about, for example, this is CD quality sound, or this is CD quality music. That's saying that the music has been preserved to a certain level that you can't really tell the difference. But there is some loss of information, whether you can perceive it or not, there is loss of information if you are going from the analog world. And the other big part is that DSP systems suffer from finite precision. In the analog world, for example, you can represent any number You can say I'm going to represent 1.21158. You can keep on going. But a DSP system always has a finite precision. So a DSP system, an 8-bit system, has only 2 to the 8, 256 levels, or 256 different values that it can store. If you have an 8-bit system, it can only store 256 values. So a number between, let's say, 0 and 1 has to be mapped to only 256 different values. That process is called quantization, which we will also study in this course. And the third is that DSP systems tend to, although this is really going down, tend to consume more power. Okay. So these are all the disadvantages of DSP systems, and I laid down the advantages also. So why do we still want to talk about DSP systems and not analog systems? Or because the advantages of DSP system are much, much, much better than the disadvantages. And also, with recent advances, this is only getting better. So 20, 30 years ago, you used to have 8-bit computers, then you got 16-bit computers, then you got 32-bit computers, now you have 64-bit computers. So 64 is 2 to the 64 levels. Things are only getting all the disadvantages that we have talked about. Their effect is becoming less and less and less. Okay. And that's why we really prefer DSP systems over analog systems. So I'll end the discussion of what is signal processing by giving you a really big picture of DSP. So the idea is that you understand the different ways in which DSP comes into our life. And of course, in this course, then we'll look at some very, very tiny fraction of these things. So DSP systems, of course, they involve always, there is a notion, DSP systems have to, a system means there is an input. So DSP systems act on either physical or man-made phenomenon. That's the starting point. If you want to build a DSP system, that is always the starting point. What are you looking at? So for example, if you are a seismologist, you are looking at seismic data or seismic activity. If you are at Facebook, you are looking at Facebook interactions. Not in the sense of you are interested in who is doing what, but you want to make money for the Facebook as a company, right? And once you look at this man-made or physical phenomenon, then the first question you ask is, how do I measure this phenomenon? How do I acquire the phenomenon? So this is called measurement, how you measure it, how you acquire it. And that falls under the category of sampling theory. Okay. That is something that we will study in this class, a brief version of that. If you are talking about voice and you want to process voice, how should you acquire that so that you can store it in a system and process that? And of course, to answer that question, the interface is always some device. It could be in hardware, it could be in software, and so forth. If you are working at Facebook, you are asking, how do I measure those interactions? Should I measure the likes? Should I measure how much time they spend on a page? Things like that, right? Now, once you do the measurement, then you have after this, you get a discrete signal. So before this, you could have a discrete signal or an analog signal. After sampling, you almost always have a discrete signal or a digital signal that is ready to go into a DSP system. And then you ask, now that I have the sample signal, how should I analyze? So the first part is measurement or acquisition. The second part is analysis. How do I analyze the phenomenon? And that's where algorithms come into play. Based upon the area that you are working on, there are many ways you can do the analysis. In this class, we will look at what is called discrete Fourier transform. We'll look at DFT-based analysis or processing. So that could be one thing, or you could also be interested in not only just analysis, but also some manipulation of the signal. For example, for a music signal or an image, you could be interested in, you have a large size image, you want to make it small so that you can send it over email or using MMS or whatnot. So another question you can ask is how to manipulate the phenomenon. And that also operates on discrete signal. Again, there are many ways that you can do that manipulation depending upon how advanced you go into signal processing. In this class, we will do what is called digital filtering for manipulation, which mainly works in terms of manipulating the frequencies of the signal. And then in some cases, after you have done all of that, you might be interested in how to reconstruct the phenomenon. So here you need another device. Which is a combination of hardware, software. So what do I mean by reconstruct the phenomenon? For example, if you are again talking about music recording, music originally is analog. You figure out how to sample it, then you processed it, then you stored it on a CD or some other format. But at the end of the day, for music, you want to listen to it. So you are interested in reconstructing the analog signal that you started with. So if you do that, then that's called reconstruction, and we'll study that for a specific case in the context of reconstruction part of the sampling theory. We'll focus on very special cases. For example, if you are looking at, of course, MRI imaging. MRI imaging is not doing imaging in the traditional sense. They are using these magnets to align signals in your body, and they are making those measurements. But at the end of the day, you want to display something for the radiologist, right? That's the reconstruction aspect of medical imaging. Or if you have a CT scan. Now, we want, of course, learn about those reconstruction phenomena. But in many signal processing systems, you are not only interested in manipulating or processing, you really want to, at the end of the day, display something, reconstruct some phenomenon. Okay, that's where reconstruction comes. Now, this is the big picture where you may be working on all components, or you may be working on a small component of this big picture. A system may have all of these pieces in place. It may have only one piece in place. We are only going to touch upon specific realizations. We'll focus on a special type of sampling theory, a special type of processing called digital filtering, a special type of analysis which will look at DFT analysis and reconstruction. Now, I want to just clarify one last thing. The focus of this class in this big picture is on the mathematical underpinnings and implementation in software. Despite what the name implies, DSP, at least in this class, it is not a hardware class. It is not VLSI class. It's not circuits class. Because we are talking about processing in a digital system, we'll understand how to address all of these things mathematically, and then work with them. Our tool will be MATLAB. So we'll be using MATLAB very extensively, and also in your labs.